you will take the third exam on Monday. This is a review for the exam. Let's try to solve on all the exam set. Number 1, use cylindrical coordinates to evaluate triple integral over E y squared dv, where E is the solid that lies within the cylinder above the plane z equals 0, which is the xy plane, and below the cone. Okay, for this problem, now in 3D coordinates, x direction, y direction, and that is z-axis, and inside the cylinder, so we have here radius 2, and above the plane, xy plane, and below the cone. The cone has a shape of like that. It's now 45-degree angle, and like that. So that we try to find the integral over this E that's below the cone and inside the cylinder and above the xy plane. Okay, for that one. And for triple integral, and for particularly for cylindrical coordinates, you have the polar region, so that will be the polar region on the bottom, and the now vertical direction. So that is from bottom Z to top Z. Okay, from here we have top Z equal square root of x squared plus y squared. So the given integral is integral over the bottom, which is d, and from bottom z, which is 0, and above the plane z equals 0, and top z is square root of x squared plus y squared, and the integrand is y squared and z direction, and then now dA, right? That's the formula you have to evaluate. Okay, now this is z direction integration, and that is independent of z, so that this one times the length is the integral. So we have here double integral, and y squared we have, and square root of x squared plus y squared, and dA. Now we focus on this bottom D, which is a polar region. Angle is from 0 to 2 pi whole cycle, and R is from 0 to 2. Okay, from 0 to 2 pi, R is from 0 to 2. That is y is r sine theta, so the r squared sine squared theta, and this is r, and we have now scaling factor r. We have to have this one, and dr d theta. Okay, this is separable, so we can get here from 0 to 2 pi sine squared theta d theta, and integral from 0 to 2. Okay, now r to the 4. Right? Okay, now from here you can evaluate quite easily, and by using the formula, this is half 1 minus cosine 2 theta. The cosine 2 theta will make 0 contribution. So from this one, you will have a pi. Okay? And from this one, now 1 over 5 and r to the 5. And from 0 to 2, that is a 32, and 32 pi over 5. Okay, that's the final answer. Let's go to the second problem. Use the spherical coordinates to evaluate this integral, where E is the portion of unit ball that lies in the first octant. Okay, that is octant, so that now angle theta will be 0 to pi over 2, and phi from the north pole in spherical coordinates will be 0 to pi over 2, right? And this is definitely a spherical region, so that given an integral is simply, now rho is from, but first your outmost integral is from 0 to pi over 2. There's phi from the north pole, and theta is mid one from 0 to pi over 2, right? And then rho is from, okay, that is from 0 to 1, right? And then here the integrand, okay, this is rho squared, so that eventually integrand is rho, okay, e to the rho cubed. We have exponential function here, so that e to the rho cubed. And then scaling factor is rho squared. Can you remember that? And then here another one is sine phi. And innermost one is the rho, mid one is the theta, and outmost one is the phi. Right? Now these are also separable, so you can get the solution through the formula. And for phi, okay, we have sine phi from 0 to pi over 2 sine phi d phi times theta, okay, theta independent, so we get pi over 2 immediately from theta integration, and rho integration, which is from 0 to 1, and rho squared e to the rho cubed and the rho, right? Okay, for this one, now the value must be 1, and we have a pi over 2, another constant here, and antiderivative of this one must be 1/3 of e to the rho cubed, and from 0 to 1. So that if you make a derivative, then okay, 1/3, not 2. Then here the derivative of this one will be 3 rho squared. We need 1/3 to match the equal. Okay. So that is now coefficients as pi over 6, and once rho is 1, then the value is e, rho is 0, then that is 1. So that we have this result. Okay. Third one, make an appropriate change of variables to evaluate the integral over r, double integral over r e to the xy, where r is given by the inequality x absolute value plus y in modulus is bounded by 1. Let's try to visualize the region R. Okay, there's x direction, y direction. Now you can consider separately the cases here in the first quadrant and second, third, and fourth. And for example, in the first quadrant, that will be x plus y equals 1, which is exactly this one. This is 1 and 1. For this second quadrant, that is now minus y, minus x. X is negative, so that, yeah, there is minus x plus y equals 1, which is now x is minus 1, y is 1. So that one. The same way, and third one, that it must be x minus y equal 1. So that one. And in the last quadrant, that must be minus x minus y equals 1. No, I'm sorry. That one, yes, x is positive, so that we have that one, right? For this one, oops, that is x is negative, y is negative, so we have to put here x is negative and positive. Okay, so we have that. So R is this region. That's R. Okay, of course there's minus 1. Okay. Now overall, we try to get the integral. Now we have to introduce the appropriate change of variable. Now we can introduce, for example, now also it has x plus y. So we may introduce u equal x plus y. Also here we have x plus y. That is x plus y is equal 1. That's x plus y is minus 1, right? And the other one is x minus y. So the v is x minus y. Let's try to consider that, right? Then xy can be expressed as a function of u and v in this way. Just adding these two, we have u plus v is 2x. So we have x equal half u plus v, and y is, after subtraction, and we have 2y is u minus v, so that half u minus v, right? So that's the transformation we found. Along with that transformation, okay, the region Q, the pre-domain, can be found in this way. Okay, its transformation, that is the transformation T here from the pre-domain in UV coordinates. That's U and V. Okay. Now if we introduce this one, then that is same as U equal 1. Let's try to use red pen. X plus y is U, so that this one is same as U is 1. Now x minus y is V. Now that is V is 1. X plus y is so minus x minus y is minus u. Minus u is 1, which is same as u is minus 1. Okay, that is minus x plus y is negation of v, so that there's a v is minus 1. Okay, this line is u is minus 1. Okay, u is 1 and v is minus 1, v is 1. So that by using this transform, you'll get the region Q in UV domain like that. V is from minus 1 to 1. U is from minus 1 to 1. That is Q. Right? Now, the integral can be done over Q, but you have to find the scaling factor. So there's in the notation, there's round xy over round u and v, right? That is the determinant of the metric x u derivative. That is a half. X v derivative, again half. Y u derivative, half. Y v derivative, minus half. Determinant is minus quarter, which is minus half. Okay, we have that. Now, in integral, absolute value of this one will be used. So the given integral is now integral over Q, and the integrand is e to the x plus y is u, so the e to the u. And absolute value of this Jacobian is half, and dA, right? Okay, Q is now rectangle, and in each direction -1 to 1, so that it is separable, and half can come out, and now -1 to 1, here dV times u is -1 to 1, e to the u, and du. Right? Okay, so there's a half. This integral is 2. That one, antiderivative is the same as original one, and we are evaluating -1 and 1, and this one makes 1, and then from here we have e minus e to the -1, right? That's the final answer. Evaluate the line integral. Okay, for that one, for scalar functions, once we try to evaluate, then now, okay, integral over c f ds, then once c is parameterized, then and then the t is moving from a to b, then that must be f r of t as a function of t. You can write in this way, and then okay, we have here a formula, and then now r prime, the length, that is scaling factor, and dt, right? For vector field, once it is parameterized, then we have here integral from a to b f of r dot r prime dt. And line integral of a vector field is we are trying to get the tangential component of the vector field along the line arc length segment, right? Okay, that's the background and formula. And for part A, so that we have to get the scaling factor. Okay, that is minus sine t, and that is now cosine t, and this is 1, so that r prime, the length is square root of this square root plus that square root, which is 1 plus 1, so that square root of 2, right? So the given integral for part A is the same as integral. Now this parameterization is from 0 to 2 pi. T is moving from 0 to 2 pi. And y is this one, sine t. And then sine z is t. So one more sine t. And we have here, now that is the integrand. And we have a scaling factor, square root of 2, and dt, right? Okay, for that one, square root of 2 will come out, and we can use the formula from 0 to 2 pi for that one. There's half 1 minus cosine 2t dt. T is moving from 0 to 2 pi, then 2t is moving from 0 to 4 pi, so that it will make full 2 cycles, so that halfly positive, halfly negative, there's no contribution for the integral. So we may ignore this part, and integrand is a half and 2 pi, so it is pi. We have square root of 2 and pi. Okay, that's the answer for part A. Now we'll go to part B. And here, f is given y okay, zyx, and c is given by here in this way, and t is moving from 0 to 1. So again, by using this formula, and for part B, the given integral is same as now integral from 0 to 1, f of r, okay, f of r, that is, okay, z, which is t cubed, and y, which is t squared, and x, which is t. Now r prime, okay, derivative is 1. For that derivative is 2t. For this derivative is 3t squared. Okay, we have to evaluate this one. Now from 0 to 1, that is t cubed from this product. For that one, plus now 2t cubed. And from the last one, we have 3t cubed. Okay, so total 6 from 0 to 1, t cubed dt. So 6 times 1 over 4, t to the 4, evaluation from 0 to 1, so that we have 3 over 2. That's the final answer for this one. Number 5, vector field is given in this way. Now, first question is prove that the vector field is conservative. Okay, it's differentiable, continuously differentiable. So the conservativeness is the same as q, x derivative is same as p, y derivative. So if we check that, then we're done for part A, right? Okay, part A. Now q, x derivative. Q is the second part. Now x derivative is e to the y plus cosine x. How about p, y derivative? Okay, the first part, y derivative. From the first one, we have the same e to the y, and y derivative, then this portion is kind of constant, and cosine x. They are the same, so that it is conservative, right? Now, is conservative, so that there must be a function f such that f exists, so we may use the notation existence of f such that gradient of f is given vector field. That means the first component, which is x derivative of f and f sub x, that must be the same as the first component of that vector field, which is e to the y plus y cosine x, and the second component, which is f sub y, and the second component of vector field, x e to the y, and plus sine x. Okay, we have to solve these two equations to find f. It's a standard technique, and number 1 equation, number 2 equation. Then from 1, we make x integration, then f. F is now x e to the y. X integration, we are working on now x integration, and plus y sine x. Right? Cosine x becomes sine x in integration. And we have to put a constant, but the constant must be general. And we put here g of y, a function of y, so that if we apply x derivative, then it will become 0. So this is general constant for x integration, right? So we have to decide now g of y. If we decide g of y, then that's it, right? To get g of y, let's try to make Now y derivative of this one, then x e to the y, and now that's a sine x, and g prime y. Okay, we compare this term with the second one. Already f sub y must be this. So comparing with the equation here, we get this portion must be 0, which means that g of y is, as a function of y, it must be constant. So we say general constant k. So we conclude here, okay, f is, now g of y is constant, so that there is x e to the y and plus y sine x and a constant k. Okay, that's it. Now how about C? Okay. Now we want to evaluate the line integral of the vector field where C is parameterized in this way. Now, once the vector field is conservative, and if we can find the potential, then the integral, line integral, can be evaluated along with the potential endpoint at beginning point. Okay, so the already we know the potential, and we have to find endpoint and beginning point. The endpoint r pi, t is moving from 0 to pi. Alpha is the terminal point. Pi is pi, then is that is minus 1 e to the pi minus e to the pi, and pi, then there will be 0. Okay. Now, how about the beginning point? Okay. T is 0, then there's 1, and again, this is 1. So it's 1, T is 0, then 1, 1. T is 0, then 1, 0. So there is 0. We found that. So the given integral over C f dr, which is same as f at the terminal point minus e to the pi and 0 minus f 1 and 0. Okay. X is minus e to the pi, y is 0. Okay, y is 0, then this portion is 0. X is e to the minus pi, so that minus e to the pi times e to the 0, which is 1. So that is this one. Minus f1, 0. X is 1, y is 0. X is 1, y is 0, which is 1. And then this one is 0. So that's the final answer. Okay. Okay. Here we have the final problem. Use the identity, an application of the Green's theorem, and area of region is the same as double integral over the dA. By using the Green's theorem, we have this formula along the boundary x dy. So we'll use this one, and piece by piece along the boundary we'll try to compute, and we'll finalize the area of the. Okay. For this one, we have 3 pieces, and now this one, C1 and C2 and C3, there are 3 pieces. Okay, x dy in y, there's no change, so that contribution from this part must be 0 quite easily. How about this one? You have to parameterize this one, so that, okay, so C2, second part, r of t you can parameterize this one in more than one way, but we'll do one way here. 1 minus t, the beginning point, which is now for n0. Okay, x is for y equals 0. And end point is t, and that is 2, 2. Of course, t is moving from 0 to 1. That is a parameterization. So we can get here that is same as 4n0. And okay, so we subtract, then that is now t, and here minus 2 and 2. We subtract this one from here, and we have t here. Okay, so that is now 4 minus 2t and 2t. So integral x dy is along C2, same as integral from 0 to 1. The parameterization is here, and t is moving from 0 to 1. X, which is 4 minus 2t, and dy, y prime, 2, and here dt. If you compute this one, you'll get the value 6. Okay, you can do it quite easily. Now, how about C3? For that one, you may use another way of parameterization. Okay, that equation is x equal y, or y equal x. If x is t, then y is t. So you may get x is t and y is t, but now because the direction is from here to there, now t is from 2 to 0. So it's going down. So the integral C3 in positive direction x dy must be now from 2 to 0. So as t is moving from 2 to 0, x is t, and y, that is dy, that is y prime 1 dt. Right? So that is half t squared, and 2 and 0, that is minus 4, so that minus 2. Okay. So if we add here 3 values, 0, 6, minus 2, then that must be 4. Area of this region is 4. You can easily check that the bottom length is 4, height is 2, times half, so it is 4. So we got the right answer. But by using the Green theorem and this formula along the boundary, x dy, integration, you can get the answer. You may use numerical value. Okay, let's try to do it once more using numerical technique. For each portion of boundary, mid value of x and change in y. Okay, let's try to do that. Mid value of x is 2 and change in y is 0. Okay, mid value for this one, mid value is 3, mid value of x is 3, change is in y from 0 to 2, changes to 2. Now for that one, mid value of x is 1, okay, that is 1. Change in y is now that negative 2 from 2 to 0. So that is a minus 2 is multiplied. So that is now 0, that is 6, and that is minus 2. So we have exactly same result, and we can sum them to have 4, right? Okay, so numerical technique is much more convenient, and you can do it much more quickly. Okay. Okay, that's the end of review. Thank you.